Okay, hey everyone, welcome back to nano-optics. So at the end of last class, I gave you guys a few problems to work on, and so the first thing we're going to do today is just go over the solutions to those problems and see what else we can learn from them. So the first thing I had you do was simulate a bunch of gold spheres and then look at the absorption and scattering spectrum of those spheres. And I'm just plotting the result here for a whole bunch of wavelengths. This is starting from 10 going up to 60 nanometers, and this is the absorbance cross sections. So if you remember, I said last time, kind of two things can happen once light interacts with a small particle and excites a collective oscillation. Either it can ultimately decay into heat, or it can give rise to rescattered radiation, and so absorbance is a part of that will ultimately just become heat. And you can see, as the size increases, the absorbance spectra increases in intensity, as you would expect. There's more atoms, more electrons to participate in the resonance, so this absorbed cross section gets higher. It also redshifts and starts to broaden, and this is not as obvious why this would happen, but mainly. What happens is there's a few different processes that give rise to kind of this broadening that you see in these peaks, and it really just depends on the lifetime of the collective oscillation. So at really, really small sizes, what starts to happen is you have damping off the surface, and so this is just as the electrons reach the surface, they can be scattered by different kind of states on the surface, and this can cause it to lose energy. And then as you get really, really big, then another thing starts to happen, and it starts to more effectively couple to the far field. So this just means that the light scatters more efficiently and more quickly. And so actually, in this case, the narrowest peaks are kind of somewhere in the middle. So then if we look at the scattering, I was doing this yesterday, I don't know. It's just slow. So scattering shows pretty much the exact same trend, but what you notice for the scattering is actually it increases a lot once you get to a certain size. We can see, like, for the 40, 50, and 60 nanometer spheres, the scattering is much, much more intense than for all of the smaller sizes. And then if we just, but again, it shows like the same trends of broadening and redshifting. But if we plot this ratio, we see that it's not conserved across all these sizes. In fact, for small spheres, 10 nanometers, pretty much absorption dominates. It's orders of magnitude bigger than scattering. But by the time we get up to 60 nanometer spheres, actually, scattering is the dominant process for decay of the oscillation. So this kind of tells you, depending on what you would want to use these things for, you may want, the size can be an important variable. Whether or not you want to make a lot of heat, or whether or not you want to use it for imaging or something, and take advantage of this far field scattering. The next question asks you to make an anisotropic object. So it asks you to kind of elongate one of these spheres along a particular axis, and then look at the optical properties when you did that. So what I'm showing you here is the electric field around the object by one of these elongated gold rods. And in this case, I've polarized the electric field in this direction here. Now this makes sense because you'd expect that the direction that the electric field is polarized in, the electrons are going to be driven in that direction, and therefore the field intensity will be highest in the direction that you paralyze the electric field. And you can see that. You get the strong mode pretty much along the whole length of this ellipsoid here. And if you just look at it, you see the field intensity. It's actually pretty broad, I would say. Like the field, the highest field intensity stretches all the way across this whole object, and the max field intensity is, something like 4, on the order of 4. Then if I look at the long axis, if paralyzing the light along the long axis, you can see this, it's much more squeezed, right? Like everything is really strongly localized to kind of the tips of the rod. And this is a very general effect. Like if you polarize light along an object that has any type of sharp feature whatsoever, just because of screening, you'll find the charge tends to build up around these sharp corners, basically. And this has a very strong effect on the field localization. As you can see here, the field's all kind of squeezed just to the ends of this rod. And the max field intensity is 2 orders of magnitude higher than it was when we had it polarized the other way. And so this is a really good way if you really want to get very high field intensities on the nanoscale. Then making sharp features, it's pretty much directly related to how much curvature is in the structure that you're dealing with. If you look at the spectra of these, which I haven't plotted here, but you'll see that the resonance for the short mode, the one where it was polarized along the side, ends up looking something like this. This is probably about 500 nanometers. So this is very similar to just like the sphere, basically. It's a very similar resonance to the sphere. And then the other mode has a narrow, sharp, and much stronger peak. I can't remember exactly, but somewhere in the ballpark of 600 to 800 nanometers. Again, the reason for this is just the higher radius of curvature will cause a redshifting of this peak. And then the peak turns out to be much narrower and much more strongly scattering than this peak. And this is mainly because, so like I said, like the narrowness as well as the fraction that gets rescattered kind of depends on how the collective oscillation decays. And it turns out that for gold, the spectrum of single electron transitions looks something like this. So this is actually, it's called DSP, but it's exciting an electron from the valence band of gold, which is a d orbital, if you will, and then to the conduction band, which is sp hybridized orbital. So it's just excitation of single electron transitions from filled orbitals into unoccupied orbitals. So the spectrum looks kind of like this. So when you have peaks that are kind of in this wavelength range, actually you lose quite a bit of the collective oscillation to excitation of these single electron transitions. So this peak is broader and more strongly absorbing. And then when you change the structure and you shift everything out of resonance with this, you get a much narrower and more strongly scattering peak. And so that's what happens. That's the, in a nutshell, that's kind of the effective shape. Now the third question, I may have been, so the third question basically asks you to think about the ability of these things to act as kind of nanoscale sensors. And the way that it asked you to do this was to make an object that looked like this. This was actually, I don't know, I might have been unclear when I was explaining this to you guys on the board, because I think I misremembered what I had written for the problem. But basically what I asked you to do was to make a core spherical particle of silicon dioxide and then to coat it in a thin shell of gold. And then it basically asked you to change the refractive index of the environment surrounding the gold, and then it asks you to look at how the spectrum changed as a function of the refractive index of the environment. And so I have this, there's a paper here that I took this from, and this is the data in this paper. You can see that as the refractive index of the environment becomes larger, the plasma resonance peak redshifts. And if you remember last time, we kind of derived this expression for the polarizability of a sphere, and we said that it was something like when epsilon omega of the particle equals to -2 epsilon of the medium, we'd get a resonance. And you'd expect this as you increase the refractive index. And the other piece of information you need is that epsilon p looks something like this, where these are negative numbers. So it was increasingly negative as we went to increasing frequencies. So these two things together is how we get to understand this effect here. Oops, there we go. So this is plotted. So you can see that these shifts also can be quite large, right? Like, so if changing the refractive index from 1, which is vacuum shown here, to 1.6, which is like, I don't know, some carbon, like something that was maybe graphite or something, that would actually cause a plasma resonance shift of 120 nanometers, which is that's pretty massive. If the other thing the question asked you to do was to look at, as a function of how thick this gold shell was, look at how sensitive it was. So basically, how big of a shift in the wavelength do you get as a function of the dielectric constant or the refractive index? They're related, so I'll sometimes use them interchangeably. And you can see that for very, very thin shells, you get a much higher sensitivity. Now, this might not be totally obvious why this is, but it turns out that the reason is because this is a hollow object of gold. I'm not going to draw the silica, it doesn't really matter. But because this is a hollow object, it turns out that you can actually have get plasmon resonances between any metal dielectric interface pretty much. So there'll be a mode that is supported along the outside interface, the interface between the metal and whatever your medium is. But because this is also dielectric, there's actually a mode that can propagate along the hollow inside of the interface. And you actually see this a lot when people make kind of macro scale sensors based on this. They'll often use kind of just arrays of holes. They'll take a big sheet of metal and they'll just cut holes in it. And these can actually be pretty efficient, have pretty efficient plasmonic properties. And so what happens in this case is the resonance that you see is not actually just a normal sphere resonance. It's the resonance that results from the coupling between this hole resonance and then this outer sphere resonance. And so if you think about it, there's actually two possibilities here. These two can be completely in phase, like I've drawn here, or they can actually be totally out of phase, like this. And basically, in this case, they'll cancel, and in this case, they'll add. And so if I were to draw the energy levels of like the isolated things, as well as the coupled things, it would give rise to, like, in a way, two new states. You could think about it. One that was a result of the constructive or the destructive interference that was higher, as a result of the constructive interference that's lower in energy. And so that's why the spectrum of this too, if you were to plot it, you can see even when it starts, it's like 600 nanometers. So it's considerably redshifted relative to a sphere on its own. And that's also why it's much more sensitive. And that's why it gets more sensitive as this gets narrower and narrower, because this coupling gets increasingly strong. And so I think that's it for the answers to the questions. Again, I put literature references in that Dropbox if anyone wants access, kind of explaining all of this stuff in more detail. But for now, let's focus on what we're going to do today. So for today, we're gonna go back to the same place. Go to NanoHub. Go to Tools. On the tag again, it's still under DDA or DDSCAT. But this time there's something that's called Nano DDSCAT Plus, and that's what you want to use. So this is basically just going to let us draw whatever we want and then just simulate it. So there's kind of four things in this kind of workflow that will happen when you open this. The first one is Blender. It's the drawing program. So this is where you'll generate your shape that you're going to do your electrodynamic simulation on. The second thing is this convert tool. So this will take this shape and then turn it into an input that will work for doing the simulation. The third one is going to be very much like what you did last time. It will just be the interface for doing the simulation, and then this will let you download any or all of the, the object and the output and all that stuff. So the first one you're going to open is this thing called Blender. So Blender is actually a 3D animation program. But it's pretty good, and it has kind of all the features we were looking for to make a quick and easy interface for doing these kind of simulations. And so when you first start it, always what will happen is it'll load this exact scene. It'll have a cube centered at the origin, and then it'll have drawn in these two objects here. And so one of these is representing the direction of propagation of the incident light. So that's this one that says incident light. So the light's going to propagate along this axis here. And then the other one represents the polarization of the electric field. So the electric field right now is polarized along this direction. Now, if you guys have mice, that would make this a bit easier because basically the center key or the roll ball is kind of holding that down is how you rotate things around the scene. I think there's also key shortcuts to do this. I can't remember what they are. You have to Google them if you don't have a mouse. But I mean, definitely if you have a mouse, it's considerably easier. So you hold down. If you hold down the center scroll wheel key, this will let you rotate around other stuff. And then if you hold Shift and do this, then that will let you drag the whole. Oops. In case I drag too far away. This will let you drag the whole thing so that you move it like this instead of just rotating. The next thing that's important is so this ball in the bottom here lets you select the kind of view that you have, and I suggest using wireframe. It's kind of easier to see what you're drawing if you change everything to wireframe. The next thing you can do is if you hit delete, that will get rid of objects that you've selected. And then if you hit Shift A, it will let you add kind of standard objects in this of these preset pre-built objects here. Okay? And the idea for like drawing any arbitrary shape is to kind of start with a shape that's close enough to what you're ultimately trying to get to, and then kind of modify it. And the way that we'll do this, okay, so there's two modes in this drawing software. One of them is called object mode, which is basically for moving objects around, and then one of them is called edit mode, which is for manipulating objects. So if you click on this bottom menu here, you can switch between object mode and edit mode. So once you switch to edit mode, then it'll kind of change the look of your object, and now all of a sudden I can pick any of these vertices and manipulate them, like this or something maybe. So then I can like drag them in any direction I want, like using these arrow keys. You can also hit G, and that will just let you freeform drag something in any direction. Oh, I should also mention, selecting things, you have to right-click. Don't left-click, right-click. Always right-click to select things. You can also select something in here and then just click delete, and then it will like completely delete these particular vertices. So the only thing to keep in mind is if you start deleting a whole bunch of vertices, you actually need to still redefine the faces. So the way this is going to work is it's going to expect that you have a completely closed object because it's going to try to discretize it to make the input for the DDA. So if you delete a bunch of stuff, you need to then select a bunch of vertices on the edge of where you've deleted, and then press F, and then that will make a new face, to replace whatever one you may have deleted. So just make sure that you select vertices around stuff that you deleted, press F. If you want to select a whole bunch of stuff, you can either hold down Shift and select them, or you can hold down Control and it will let you draw these types of, you can draw, you can make selections by just drawing, areas like that. And so that's the basics of how you draw shapes. You can draw, you can make a whole bunch of shapes, or you can make one shape and then look at it. Once you have kind of a shape that you're pretty happy with, you can then adjust the direction of the electric field relative to the shape. And again, so the reason you might want to do this is because, like you recall, I said normally, like if you have sharp features or something, then that will tend to give rise to these very, very strong modes when the light polarization is along those particular features. And so so if I make something like this, like let's say this triangular prism here, then I might not want the light to just come along this axis. Maybe I want it to be along parallel to one of these corners maybe. And so what I can do then is there's these built-in macros. Here on the left, and you can see one of them says rotate lights. So you click on that, it'll open up this sphere, and basically by grabbing any of these colored kind of wheel things, it will let you rotate the polarization in a specific axis. So I think I'm gonna put it so that the light goes along here, and we'll hit this tip kind of, and then excite whatever mode is aligned with this tip. Once I've done that, there's one that says lock light axis, and then you can hit the final one that says export object. So this will export the object into a file folder that the next file convert tool knows how to find easily. And so all you do is you go to choose object file, and there's one that just says Blender file, and this will automatically just use whatever the most recent Blender file you just made was when you hit export object. And then obviously you want to send it to the next step to send it to DDSCAT main, because that will let you do the electrodynamics part of the simulation. This part's kind of confusing. So basically what this is asking you is along the longest dimension in my object, how many dipoles do you want to put along the longest dimension? So you remember I just drew like a triangular prism, kind of like it was much longer along this way than kind of this side. So it's going to be like this side will be the longest dimension. So it's asking me how many points do I want to put along this dimension. You'll see it's gonna generate an output that you can look at, and you can kind of count how many dipoles it put along other things, just to make sure that the dimensions are what you thought it was. But for now, I think I'm gonna put 40. That's should be fine for this object. Then the next thing you really want to don't click this box. I'm not even sure what it does, to be honest. The display 3D output is important. You're going to want to click that because you're going to want to check and make sure that mainly it's if you miss a face, if you miss defining a face in the previous step, then it's not going to know that that's a boundary, and then it's just going to keep putting dipoles for like a whole, so your shape will look really weird. So you want to check the output. Also, this button allows you to separate dielectrics for different shapes. So basically this means that if you drew two different objects and you want them to be made of two different materials, then you would select this. Because if you don't select this, it's going to automatically assume that everything is made of the same material. Okay? So if you have different objects, then you want to select, and you want them to be made of different stuff, then select this one. And then you just hit the convert button, and then it'll make the input. And you hit this 3D rendering button, and it will show you how it discretized your object. So you can see, so it's going to have 40 along this way, and I'm going to define these later in the next step to have 1 nanometer spacing. So it's going to be 40 nanometers long this way, and the thickness is 1, 2, 3, 4, 5, 6, 7. So it's going to be 7 nanometers thick for the next step. So yeah, I mean that's pretty good. And again, you can download and save these files to make sure that everything that how big your object is really after you drew it. Next step, you'll just go to the third thing, which is the DD-scat. So now instead of picking any of these built-in shapes, you're just going to pick import shape from the latest convert tool thing. And then here again it asks you, you just defined how many dipoles you put along your long axis. Now it's asking you how do you want them spaced. So I'm just going to say 1 dipole per nanometer. That's usually a pretty good resolution for most of these things. So really kind of the previous question, if you're assuming you're going to do this resolution, it's kind of asking you how long is the longest distance in your object in nanometers. And then now for target rotations, we can just see you just want to use the incident light that you defined in Blender. So you use that one because then you know how you polarized it. Number of dielectrics to use, well, I only had 1 thing, so I'm just going to use 1. It's important that if you did in the previous section say separate all the dielectrics, if you have let's say 3 different objects, you have to select 3. Even if you want them to be the same thing, you have to select 3 and then put them all as the same thing, because otherwise it'll give you an error. And then this is the same as last time. What do you want it to be in? Well, we'll put it in water, not 11, 1.33. There we go. So this is in water. Again, all of this is the same as, except for some reason. There we go. Yeah, and again, don't change this polarization because we just defined the light in the previous step to be what we defined in Blender. And again, we're going to calculate the electric field. We'll hit process. We'll hit go, and that's pretty much it. So for the rest of the time today, so I have a problem that you can choose to work on if you want, because this problem I can guarantee you that it will show you something physically non-intuitive, and I can explain the answer to you. If you want to just draw crazy things and try to make like a really high field or some weird coupling or something, you're free to just draw whatever you want and try to simulate it too. But the problem that I have suggested that I'll go over at the end of class is this one. So the problem that I suggest is if you draw 2 kind of ellipsoidal rods like this, and then you polarize the light like this, and you bring them together either end to end or side to side, both times with the light polarized in this way. First of all, how strong is the electric field in this gap relative to in this gap? And secondly, what happens to the spectrum relative to the isolated rod? Okay, does it not change? Does it red shift or does it blue shift? Okay, this is one problem, and then the second problem would be so initially I want these both to be the same thing, gold, silver, whatever, it doesn't matter. And then for the second problem would be if you do the same thing with this one where they're end to end, but then you change it, instead of being all one material, you change it to two different materials. And how does that change? So this is a suggested problem, but feel free to not do this problem. I'll tell you the answer to this at the end of, like for the last little bit of class. But also you can just feel free to play around with shapes and try to generate really strong scattering spectra, or really high electric fields, or something like that. However you wish through drawing, and then I'll come around and help you guys if you're having problems using stuff.